Welcome to the very first episode of Fun to Imagine. Today, I have the pleasure of hosting Professor Roberto Bonifetto from Politecnico di Torino, and together we'll dive into the world of nuclear fusion, exploring how we might one day recreate the power of stars here on Earth. Thank you so much for joining me.
Thank you to you.
Let's begin with the first question.
Yes.
Nature fuses very easily on stars. How come what complexities makes fusion here on Earth very hard?
And the problem is that what happens on stars is a special process that can happen almost only on stars due to the conditions that develops in the stars. So there we have very high pressures and very, very high temperatures. And therefore we have a suitable condition for a good confinement of the plasma. And the problem is that reproducing these conditions on Earth is very, very difficult. So the real problem are conditions to make fusion happen that are kind of natural on stars and not so natural, actually not natural on Earth.
And that is what your work is focused on, making the engineering so that this can happen.
Yes, exactly. We, as engineers, we work in order to try and push the knowledge to apply all the possible know-how and reproduce these conditions, reproducing in an engineering way these conditions on Earth. So problems of materials, temperatures, pressures related again to materials. So yes, our job, not only my job, of course, but our job is to try and push the engineering in order to achieve these conditions.
And when working on your research, your work, what drives you more, the pure curiosity to see where fusion will go, or is it more of a social goal to have clean energy for all, or is it a mix of both?
It's a mixture of the two, but I should say the second one. So the idea to try and find a solution for the energy problem. Maybe it's worth also telling you my story, because I was when I enrolled at Politecnico di Torino, so it was 2005. I was a convinced anti-nuclearist.
Oh wow!
And therefore, my studies were mainly on renewable energies. But then, while studying renewable energies, I also met nuclear. And I understood that it's not absolutely so bad. I mean, the problem is that nobody knows in general what's nuclear, what are the advantages, etc. And I started building up my know-how on that, and especially being convinced that it's not possible to go on with only renewables, at least at the current rate of energy consumption. Mm-hmm. So there's no way for humanity to go ahead without nuclear, well, with only renewables at present energy consumption rates. So I moved I moved to nuclear at mid Master of Science, and then my PhD was fully on nuclear. So for me, the curiosity is also a driver, but not necessarily only the curiosity for fusion. So my aim is to try and make people aware of the fact that nuclear is not bad. It can be part of the solution. It's not the only solution. So we should look for a mixture of sources. Renewables should be there, for sure, but they cannot be the only way. Mm-hmm. So according to me, there should be a good compromise between renewables and nuclear, which are both green sources, because also nuclear is not polluting. Mm-hmm. And therefore, what pushes me is, going back to your question, the idea of trying and find a mixture of sources, and in my case, nuclear. There should be somebody else working on renewables, to have a sustainable energy production for all mankind.
I see. And were there a specific moment, or was it over the time you realized, oh, maybe nuclear isn't that bad?
It was over the time. I mean, while studying, I started with, there were in the bachelor already some courses about nuclear fission, especially. And I understood that all the typical disadvantages, let's say, that people have in mind are not disadvantages. I mean, there are workaround to them. So it's possible to exploit nuclear source. I would not say easily, but safely at least. And so that can be part of the solution. It's not must not be excluded. So that's what drives me. The curiosity as well, in the sense that, and with this I close, what is important for me in the research, and what pushes really me, is that when I get a result, I'm the first person looking at this result. So this is kind of amazing to me. When you do a simulation or you do an experiment, so in this case me, I am the first at looking these results, and this is pushing me. So it's a kind of curiosity, of course.
So the innovation is whatever you do in
Yes,
this field is innovation.
Yes.
And when you think of it in a more scientific, ambitious way, how do you balance the scientific ambition of fusion from the engineering realities? Do they clash often?
So you mean
like the curiosity and the reality of engineering we have today? Do they clash, or is there a balance between them?
Yes, I mean they are kind of competing, but at the same time they are going on together. So I think, well, I'm an engineer, so I try to push more on the engineering side. But of course, doing research, I'm also a kind of scientist, and so I try to look for maybe basics concepts in physics or something like that, but then to reach them through the engineering. So it's compromise, let's say.
Yeah. Now, talking about engineering and optimizing, much of the work in the nuclear fusion is about optimizing the confinement. Do you think that eventually the attention will turn to how we extract the energy itself? In other words, can fusion truly be revolutionary if the main conversion method is still the steam turbine?
It's a good question, in the sense that, according to me, now the problem is to be able and demonstrate that fusion can provide more energy than what it consumes. This is the first target for almost anybody doing research on it. Forget about maybe the startups, etc. But who is doing research, this is the main goal. When we reach that point, we will see what are the real potentialities of fusion. So at that point, many different paths can open up. So you can go for the standard way of extraction of energy, and it will be already enough, I guess, because the amount of energy that can be produced by fusion is so huge that you can even extract it with 30% efficiency, and it's sufficient, it's enough. But of course, once you have the technology to reach this goal of having more energy than what you consume, then maybe you will be pushed by improving the efficiency. And therefore, you can open up, thanks to all these technologies that you developed, maybe you will be able to open up new possibilities. So I will not put any stop, let's say. So once we will be there, and hopefully we will get there, that will be another story. So from there, the fusion history will really start, and then it will be a new job, I think.
This is such a good point, because I also wanted to ask you, once we produce more energy from fusion reactions than the energy we put in to heat them, in other words, once Q greater than 1 is established, does the progress accelerate, or does the real work then start?
I think that the real work will start from that point, in the sense that up to that point, it's research, which is also work. I work in research. But from there on, there will be all the possibly different technologies that can develop from there, because once is the scientific goal of having Q larger than 1, and then you have the engineering goal of translating this Q larger than 1 into real usable energy. So there, I think that there will be a lot of work for many, even more people, according to me.
To take it into our cars, to the space, and so on.
Yes, well, yes, exactly. So transportation, ground transportation, or even space transportation, possibly.
And now I have a question on the more computational research side. Are today's simulation tools obedient to the reality, or does the plasma still find ways to surprise you?
It's also a good question, because I was born as a modelist. So my first job was to write down code lines and try to do simulations. And I was taught by my mentors that to demonstrate that your tool is valuable, you must validate it. So you must have an experiment, the experimental data, no other codes, really experiment, so data, numbers measured, to compare with, and the match should be as good as you can within a certain accuracy that you can tolerate, of course. So according to this, I should say that you will always need experiments if you want to have a good tool, because you have to demonstrate that your tool is in agreement with reality. And this is also why now I partially moved to experiments as well. So we are setting up with our colleagues some experiments here in the laboratories of the Politecnico. So yes, I would say that experiments will always be one step ahead, even though the numerical models are needed, because the experiments are very, very expensive, especially experiments when you push the technology to the limits. So the materials, the acquisition systems become very expensive. And therefore, being able to do one experiment to validate the tool and then use the tool for similar computational experiments, as we call them. So we do the experiments by means of the tool, no more by means of measurements. It can be a very important support for the design, for the optimization, for instance. So when you have to optimize something, if you are moving around with your parameters around the space that you analyzed with the experiment, then you can trust your tool, and you can replace expensive experiments by cheap simulations.
So, I mean, even if you have a fully predictive model, it seems like from now it's going to be a cost thing more than it is that experiments will always lead theory in a way in fusion.
Yes, in a sense, yes. Well, the code itself doesn't cost that much. I mean, the experiment is much more expensive. But the point is to have, I mean, once you have a reliable tool, yes, but to reach the reliable tool, you need experiments. Yes, and also especially for the case of a plasma, which is not exactly my main research topic. When you have plasma is something that in the tokamaks is something which is moving, so it can give birth to instabilities. So it's something very difficult to simulate reliably.
We talked about the simulations, and now there's a growing talk on artificial intelligence. Do you think that at any point, imagine a reactor that is continuously learning, continuously tuning itself the way neural networks do self-optimization?
Yes, in the sense that we are already working on that track, in the sense that we are trying to use artificial intelligence coupled with experiments to improve the learning from the experiments, also for the plasma confinement and prediction of plasma behavior. So having a reactor that has embedded artificial intelligence to improve its stability is something that, as I said, we are working on. And again, artificial intelligence had a very steep progress in the last years, so it's not possible to put against stops or so I think it will permeate our lives more and more, in a good way or in bad way. But it's like internet, you know. Internet, when it was discovered, it was only discovered. It was invented by CERN, It was something that was prepared for a good purpose, but then there is dark web, there is all the negative part, and also the too heavy use of internet as well. And artificial intelligence, I think, will be the same. So I think it will play an important role in the development of fusion from the scientific and from the engineering point of view, because also using artificial intelligence to prepare new materials according to, again, experiments, but also to all the materials we already have around. So optimizing materials is, again, something which is being done, and it will be very important.
And it will always speed up the process.
It will speed up the process for sure. At least because it will maybe point out the attention towards specific developments with respect to others. So I think it will be very helpful.
And now thinking about the innovations. When we make fusion work on Earth, what does that enable of Earth about lunar bases or in situ resource utilization, space logistics? So if we master fusion on Earth, what does that mean for sustaining life beyond Earth?
Yes, again, fusion is a very large effort. I mentioned it before for internet, the CERN and all the LHC devices and diagnostics. Besides being useful themselves, the path to reach them was already useful because it enabled several technologies, GPS, just an example, okay? And the same is fusion. So while you try and reach the target of fusion, you enable several technologies that can be useful already immediately for other discoveries. Besides then being able to use fusion as a energy source to develop lunar bases or bases on Mars, or have energy for long journeys in the space. So this is, of course, what immediately comes to your mind when you think about having energy. So you can travel very long distances, maybe faster, maybe having, again, lunar bases. But then also all the technologies, so the materials that you develop, again, the way of mastering high fluxes or high neutron fluxes, because when you travel in space, you have also a lot of particles that you don't have on Earth because of the atmosphere. So there you are not protected. So the capability to shield these particles, gamma rays, X-rays, that we already mastered a lot, but all these new features can be used for several applications. So it's even difficult to imagine now. I mean, once you will have them, again, it opens up a new...
It's very, very fun to imagine what could happen.
Yes, exactly as for CERN. I always have in mind that reference. So while looking for the, as they call it, the God particle, well, it's not the aim is not only to get that particle, but all the technology that you develop to get there.
Are there any specific technologies or physics that was developed on the side of fusion that you wouldn't really guess would happen? Like, are there any byproducts that were unusual?
Well, I come from the field of superconducting magnets, and that's already something very important because building these huge magnets allowed to build the magnets for MRI or other applications, so medical applications, and pushing again the knowledge concerning high magnetic fields, materials. So there are already several technologies that can be used, or hypervapotron, so cooling systems for high flux components. Again, you can use them in small scale to efficiently cool maybe chips or other components in a better way. So.
More is to come.
Yes, much more to come.
In one of your research, you mentioned that the big flanges in ITER you didn't use as big flanges as you did in ITER in DTT and demo. And what were the trade-off that you did about weight, cost, or stiffness, leak risk, remote handling complexity in this choice?
Between ITER and DTT and demo. Well, ITER is an experiment. DTT is also an experiment, a smaller experiment with different target. The target of ITER is to demonstrate that it's possible to obtain more energy than what you inject. The target of DTT is not that one, so we expect to spend more energy than what you get with what we get. But the target is to develop power exhaust, so the divertor tokamak test is the acronym. So is to try and push on the watts per square meter that you can obtain and try to hit with this watts per square meter a specific component, which is the divertor, and check if it can withstand these heat loads. So the task is different. Demo has another task, which is being a demonstrator. So the possibility to build a reactor that can be the first of a kind. So you can build the first one, and then you can build copies of it, and it must produce electric energy, so electricity, in an economically affordable way. So having enough availability, because otherwise you have no reward, etc. So they are different, completely different experiments. Therefore, who is developing them, myself as well, but we will use technologies from ITER, which is an experiment optimized for the different tasks. And therefore, you will rely on what you can from ITER, but you will push most of the technologies even further, because you must build, for instance, robots for the remote handling, which are not only working but also cheap. Otherwise, nobody will buy your reactor if you have to pay more for the remote handling than for the reactor, for instance. So it's something, I mean, we must be careful about the targets of the different reactors. ITER can cost much more, will cost a lot, will not produce a single joule of electric energy. So it's an experiment. All the rest must be targeted to be also cheap. So you have to develop better systems, more affordable, etc. That's the point.
And also there are different architectures as well, and there's certainly a trade-off between them. For example, the tokamak versus the stellarator. One is where stability is enforced through active control, and when it is built into geometry itself. Do you think future of fusion will favor control through feedback or stability by design?
It's difficult. It's a difficult question, because we see now several startups growing based on the different technologies, and that's good. And that's good because we cannot bet on a single technology. We did it for many years. It only partially worked because there were difficulties that are common, and so we cannot say the tokamak didn't work because it's the tokamak. The tokamak didn't work because there are objective, several difficulties that are common also to stellarators. But of course they are competing, well, they're not competing, they are different technologies. And it's the same as fission. So when you had BWR, PWR, liquid metal, at a certain point, the market itself, the success of one or the other will make the road to fusion. So according to me, it's good having both. I cannot say what is better because it's a trade-off. So you always you have to pay something if you get something better. So stellarator is good because it's stable, it's more stable, but you have to pay in terms of complexity, geometry complexity. And it's really very complex. So it's not only a way of saying. And on the other hand, the tokamak is simpler somehow concerning the geometry. It's not a cylinder, it's a torus, so not so simple as a cylinder as in fission. But it has a less stable plasma, so we will see. We will see.
About the future again, cryogenics, they seem like the quiet infrastructure holding fusion together, yet its reliability and energy costs may define reactor economics. Do you think that the next breakthroughs in fusion will come from making hotter plasmas or from cooling matter smarter?
It's again a good question, so thank you for this set of questions because it's very challenging. cryogenics is becoming more and more important. From the historical point of view, at the beginning there was almost no cryogenics apart from the vacuum technology, because the magnets were copper magnets. So in the worst case, they were nitrogen cooled, but nitrogen is something not so difficult to prepare, liquid nitrogen, I mean. So, I mean, the precursor of DTT in Enea Frascati, FTU, Frascati Tokamak upgrade, was featuring magnets, copper magnets cooled by liquid nitrogen. Then the discovery of superconductivity dates back to beginning of 1900, so 1900, so last century. But anyway, the application to the fusion was more recent, so from the 80s. And from that point onwards, the cryogenics became an important cost for the experimental reactors. And therefore, that's an important point where to make new developments. And now with the high temperature superconductors, again, even if they're called high critical temperature superconductors, the critical temperature is not room temperature. So it's around 80K or 100K. And still, the idea is to cool them down to very, very low temperature. So 10 Kelvin, not 80 Kelvin. So that part is a challenge, will remain a challenge because of the cost, also operational cost, because producing cold means operational cost. So during the life of the plant, you have to pay electricity to pump the helium. So again, efficiency there will be increasing the temperature of the plasma is also a challenge, but you see around the world there are already reactors pushing this parameter, the temperature of the plasma, very high. So it's something already being addressed. Cryogenics we require attention for the optimization.
You also mentioned that at first you were working on superconductors and then switched those. What made that switch for you?
Well, the switch was because, let's say, my interest in research was dominating on all different possibilities. So besides looking only at innovation in magnets, I wanted to look also innovation in other fields. And this is my personal attitude, let's say. So being curious also on several different technologies, plus the involvement of Politecnico in the divertor tokamak test path, let's say, because we are shareholders. Polytechnic is a shareholder of DTT, and within this framework, I took part to several general meeting on the DTT, and therefore I got more and more curious again on different components, and I tried to be involved in the research there, with quite some success, luckily enough. So myself, with my group, my PhD students working with me, and my colleagues, we are involved on several different aspects of the machine, mainly the superconducting magnets, the blanket, not for DTT, but all at large, or the plasma-facing components, so the first wall, the cooling of high flux components, the divertor. In my case, also the thermal shield, which is that very thin layer separating the cold magnets from the hot components. So we developed quite a widespread knowledge on the reactor. So it's interesting.
And between these innovations, like you mentioned the shielding, and there are other things that you worked on, like neg pumps, CSS panels, etc. Do they ever clash with each other, and that one innovation makes the other one harder to integrate?
Yes, the key word is the integration. With the last one you said, the problem is that when you think, okay, I have a solution for my thermal shield, and then you look at your neighbors and you say, okay, there is no room for this solution. So what should I do? So it's a continuous process, and that's because even for the tokamak, which is simpler than the stellarator, integration is a big job. So it's very difficult. And integration includes also the construction. So one thing is to imagine your machine already built and you operate it, but you have to imagine that you have to build the machine. So to prepare the torus, and then the torus, you must put inside them the components, inside it the components and the magnets. I mean, the process of building the facility is already very complex. So it's really challenging, but this is why we like it. I mean, one friend of mine, he's a Russian guy working in the US. Once he asked me for a result, I told him, no, it's not simple to give you a number. And he told me, beware that simple things were already done. So you have to do complex things. And he was right, he's right.
And so, it's the fun of things, the challenge.
Yeah, exactly.
And now about the innovations and the next generation of things. Is there anything that you want to give advice, or is there anything that you would want to see from the next generation of fusion researchers, fusion engineers?
Yes, and maybe surprisingly to you is not something practical. It's more an attitude of researchers to try and be more open to the public and to explain what they are doing. Because I think that there is still a big cut between what people think and what research is doing. There is no tight contact between the two, and this is kind of barrier. So maybe people do not want some innovation because they think it's bad. This is also part of my history, as I told you. So I think it's more an attitude I want to see in the scientific people. So to be more open to do public speeches, even at low level. I mean, we don't need to go to the deep details of materials or heat fluxes or technologies, but at least to make people aware that we are confident that what we are doing is safe, is good. There are positive aspects, not only. So what I can suggest to researcher and what I want to see is that attitude. And from that, everything will come, because if people are positive with respect to your job, then you will also work in a more relaxed way, and you will get closer to your targets. So
I feel that like the general public thinks of it as black magic, but I can say with my generation, because we didn't have the prejudice that came from the generations before us, we tend to be more open to these things, and because we grew up with it, we had them pretty much all of our lives. I mean, they weren't as complex as it is today, but
I totally agree with you. I see this complete change in the last less than 10 years in the new generation of students coming to Politecnico. This change of attitude. You are not, as you said correctly, you have no prejudice on this, and that's good. So we have also to do our job in trying to permeate more knowledge about what we are doing and why. And I think this will be a positive chain that will lead us, as I said, to closer to our targets.
Thank you so much for this incredible conversation.
Thank you to you, because it was very interesting also for me. Thank you for the questions also.
Oh, well, thank you for your answers. It was a pleasure for me to host you as my first guest.
My pleasure as well.
Thank you so much, and thank you for watching Fonti in Medicine.
Bye-bye.
Bye-bye. Okay.
Thank you very much.
Well, thank you.